This lecture on atmospheric circulation is being recorded for the Oceanography course at Florida Gulf Coast University. On this cover slide, we see a picture of the Earth from space, where the atmosphere is visible as a blue haze over the clouds and the ocean of the Earth. So the atmosphere is sort of the outermost layer of planet Earth, where we're surrounded in a cloak of gas. This gas, mixture of gases, we refer to as air, and it's a mixture of different gases, primarily nitrogen gas, N2, and oxygen gas. It's about 80% nitrogen gas, 20% oxygen gas, and just a little bit of a few other gases like carbon dioxide, argon, etc. So because air, even though it's a gas, is a form of matter, it has weight and it's affected by gravity, and that's what keeps the air from just drifting off into space, is the Earth's gravity that attracts the air molecules towards the surface of the Earth. So that air is actually weighing down on the surface of the Earth, and if you were able to measure an imaginary cube of air of 1 meter cubed in size. So imagine a cube of air, 1 meter cubed in size. It's my attempt to draw a cube here, not going perfectly. That would weigh 1.2 kilograms, which is a substantial amount. So if the weight of that 1 meter cube of air is 1.2 kilograms, we can apply our understanding of what density is to determine the density of air in terms of kilograms per meter cubed. If that meter cubed of air weighs 1.2 kilograms, then the math is pretty simple. It's just 1.2 kilograms divided by 1 meter cubed. Therefore, the density is simply 1.2 kilograms per meter cubed. Now, that's the density of air at sea level, where it's most dense because all the air sitting on top of it squishes it down and pressurizes it and squeezes the molecules closer together so the air is more dense. If you were on top of a tall mountain or flying high in a hot air balloon or an airplane, the air density would be a bit lower, only about half a kilogram per meter cubed on top of Mount Everest. And that's because the air basically thins out as you get higher because it's under less pressure from the air above it, pushing down on it by gravity. So that brings us to this important concept of pressure. Pressure, like density, is an important physical concept that we have to understand in oceanography. And it's a little bit different than density. Whereas density is weight per volume, pressure is a force per area. And the force could be expressed in kilograms or newtons. In this case, we're going to apply this concept by figuring out sort of what the pressure is of a person as they're walking across the ground. Their body has weight, and that weight is applied to through the surface area of their feet if they're standing up. So we'll apply this for myself. I weigh 75 kilograms more or less, and estimated the area of my footprints is about 0.05 meters squared. So if we've got 75 kilograms applied to an area of 0.05 meters squared, we can just do some simple math and we get, I'll whip out my calculator here, 75 divided by 0.05 equals 1,500 kilograms per meter squared. So that means that were that force applied over an entire meter squared, that would be 1,500 kilograms worth of force, but because it's concentrated on a smaller area, it's less force. One interesting thing about pressure is that if you've got the same weight applied to a smaller area, that means that the pressure will be higher. So if the entire weight of my body was pressed onto the head of a nail, for example, it might pierce my foot because of the concentrated pressure. whereas if your pressure is spread out over a larger area, that's less force. So atmospheric pressure is the force exerted by the weight of the atmosphere on the surface of the Earth. And the standard atmospheric pressure, which is abbreviated 1 atm, is equal to the weight of all the air above a patch of ground at sea level. So that's a heavy weight of air. If even over a tiny patch of ground, just 1 centimeter squared in size, that's about a kilogram of weight. And because there's 10,000 centimeters squared in a meter squared, that would mean that there's a really high pressure per really high weight pressing down on 1 meter squared of area from all that atmosphere above us. Air pressure varies, as we mentioned earlier, with altitude. Basically, if you went up on the top of a mountain, there would be less air pushing down on you from above, so air pressure would be reduced. And pilots take advantage of this fact with instruments that can determine their altitude, how high they are in the air, based on air pressure. And that instrument's called an altimeter. Air pressure can also vary with weather. So even if you're not changing your altitude, changing weather systems can cause somewhat more subtle variation in air pressure. And the instrument that's used to measure those weather-related fluctuations in air pressure is called a barometer. Air pressure is measured in a variety of units. We mentioned 1 atmosphere being a convenient unit of air pressure. So basically the air pressure at sea level under typical conditions is 1 atmosphere. But air pressure can also be expressed in other units such as pascals. 1 atmosphere of pressure is equivalent to 101,325 pascals, and a pascal is equal to 1 Newton of force per meter squared. And as we remember, pressure is force divided by area, basically the force applied to an area of a particular size. Another unit of pressure that's sometimes used is hectopascals, HPA. So atmospheric pressure is 1,013.25 hectopascals. And millibars, abbreviated MB, is the most common unit of pressure in weather forecasting and meteorology. So when we look at weather maps describing pressure differences in and around a hurricane, for example, we see that pressure expressed as millibars. There are some other older units of pressure that are sometimes used. Millimeters of mercury is an older unit of pressure that's sometimes still used, and pounds per square inch is a form of expressing pressure in English units that's sometimes used still for the air pressure in automobile or bicycle tires, for example. So we're going to see if we can apply a little bit of what we've learned about the relationship between the density of air and pressure to try to calculate the height of the atmosphere. Basically, how thick is the layer of the air surrounding the Earth. And we're going to get this wrong because we're going to incorrectly assume that the air is not thinning out as you go up higher. We're going to just assume that air is a constant density until you get to the boundary between the atmosphere and space. And then we want to sort of figure out where that boundary is. Where is the top of the atmosphere? If we sort of know what the weight of all the atmosphere is pressing down on us, and we know what the density of the air is. So we're going to take this fact here that the density of air at sea level is 1.2 kilograms per meter cubed. And then we want to figure out basically how many cubes of atmosphere would we have to stack up to get to the top of the atmosphere and a resultant sea level pressure of 1,300 kilograms per meter cubed. So we would just do a little bit of algebra here and figure out, 1.2 kilograms per meter cubed times how many meters times some question mark meters would equal 1,300 kilograms per meter squared. And we know that the meters will cancel here in this multiplication, so that's how we can figure it out. So let's do this. I'm just going to divide 1,300 or 10,300 kilograms by 1.2 kilograms there. And I get the height of the atmosphere is equal to 8,583.3 repeating meters. So basically, if air were the same density that it is at sea level all the way to the top of the atmosphere would be 8,583 meters high. And we know that it's not correct because Mount Everest is actually taller than 8,583 meters. And so that would mean that Mount Everest was actually sticking out into space, which is not true. But we just kind of did this exercise as a thought experiment here. This slide here shows how pressure varies with altitude, and it shows the top of Mount Everest being 8.8 kilometers high. And as we discussed earlier, atmospheric pressure on the top of Mount Everest is only about half what it is at sea level. And the atmosphere basically just gradually thins out the higher altitude you reach. Okay, so the topic of this lecture is atmospheric circulation. So we're really not interested in just sort of what the atmosphere is like in a static form. We want to know how the atmosphere moves. And one of the things that can cause the movement of air masses in the atmosphere is differences in the density of air. If there's a denser patch of air next to a lighter patch of air, that's a sort of an unstable situation that will result in wind and movement of the air masses. And so in order to understand wind and why we get air movements in different parts of the Earth's atmosphere, we need to understand the things that can affect the density of air. What are the things that can change the density of air and cause air to movement? One thing that we know that affects the density of air is altitude. So basically air density decreases as we go higher. We talked about how the density of air on top of Mount Everest is about half of what it is at sea level. Another thing that can affect the density of air is the temperature. Warm air is less dense than cold air, so warm air will tend to rise in the atmosphere. And cool air is more dense because the molecules are moving less energetically and they're clustered closer together. And so cool air will tend to sink and fall in the atmosphere. Another thing that can affect the density of air is water content. And this fools a lot of people because people think that air that contains more moisture would be more dense, but water molecules are actually lighter than oxygen or nitrogen molecules. So when air contains a lot of water moisture, it's actually less dense than dry air. So moist air is less dense than dry air, and moist air will tend to rise. When air rises, it also cools, and the water that is contained in that air as water vapor will tend to condense into water droplets, forming clouds, fog, and rain. And the opposite can happen when air descends and warms. Moisture can turn into water vapor. This diagram here shows the relationship between some of the concepts that we talked about on the previous slide. It shows how as air expands, it can cool, and as air compresses, it can warm. So rising air will tend to expand and cool in the atmosphere. Falling air will tend to compress and warm in the atmosphere. And importantly, for the concept of wind, air will tend to flow from zones of high pressure to zones of low pressure. So various processes like differential heating and processes related to absorption or of moisture or expulsion of moisture from masses of air can change air pressure in different patches of the world, and then winds will sort of result as the air sort of flows from the high pressure to the low pressure areas. And when air flows from high pressure to low pressure areas, it results in wind. And we say that that air is flowing down a pressure gradient. This is kind of like if you had a high pressure bottle, like a scuba tank. There's very high pressure inside that. And if you open the valve, the air will flow out of the high pressure area into the lower pressure surroundings. Likewise, if you had a bottle that was a vacuum and had very low pressure inside, if you opened it up, the air would flow into that low pressure area. So basically, air flows into low pressure areas and out from high pressure areas. And the stronger the difference in pressure, the stronger the wind. Also, the closer the proximity of the high and low pressure areas, the stronger the wind. Maps like this that meteorologists who are sort of weather scientists use often show differences in air pressure with lines of equal air pressure called isobars. And by looking at the isobars and the numbers that label their air pressure, you can see where the low pressure areas are, like this one here, and where high pressure areas are. And then sort of the area between the high and low pressure is the pressure gradient, along which there will be a movement of air molecules resulting in wind. So basically, the high pressure air is going to want to head towards the low pressure center. And the stronger the difference in pressure, the stronger the wind. So where you see the isobars stacked close together, that's a steep pressure gradient resulting in strong wind. And where the isobars are spaced more widely apart, there's reduced pressure gradient and lighter winds. This is a more simple diagram that shows the same thing. You've got equal pressure in both the upper and lower diagram in all these situations, but what's different is the spatial proximity of the high pressure center and the low pressure center in the two situations. So if the high pressure center is in close proximity to the low pressure center, then the isobars are squeezed together. There's what we call a steep pressure gradient, and we get a strong wind. So if on your weather map you see the lines really clustered closely together of isobars, you know you're in for some strong winds. So back to this idea of what can create pressure differences in the air. We know that pressure differences in air masses are what drive winds, but what creates those pressure differences? Well, the main thing is uneven heating and cooling. Heated air expands and rises, creating a low pressure area, whereas cooled air contracts and becomes more dense and falls, creating a high pressure area. And this type of phenomena can happen even at the small scale of a room. If there is a heater in the room, that will heat the air and the air above the heater will rise. When it has nowhere else to go, it will spread across the ceiling of the room until it cools down enough that it can sink again. In this case, there's a cold window where it might be snowy outside, and that is helping cool the air and causing the cool air to sink and flow across the floor of the room back towards the radiator, and then the cycle will repeat. This phenomenon might seem familiar to you from the geology part of our unit, where we talked about convection in the Earth's mantle, the sort of the rising and circulating pattern of molten rock within the Earth. And although the air of the atmosphere is a very different medium than the molten rock of the Earth, the principle of convection, that sort of thermal expansion and rising, followed by cooling and sinking, that can drive this circular flow pattern is the same in both in the solid interior of the Earth and in the gaseous atmosphere of the Earth. So there is no radiator on Earth, right? There's not a giant heater on Earth that's made by humans. But what there is that creates temperature differences across the surface of the Earth is a different amount of sunlight warming the surface of the land. So the differences in the amount of solar energy that reach the surface of different parts of the Earth are related to the angle of Earth's surface relative to the incoming sun rays. If you're on the equator, the sun is basically more directly overhead, and you get sort of direct uh, solar heating baking down on you. Whereas if you are near the pole, the sun will appear low above the horizon, and you'll have sort of these diffuse, spread out rays of sunlight, and that means that you receive less solar heating. So basically, the high latitude areas of the Earth receive less uh, heating from the sun, and the low latitude areas of the Earth receive much more heating from the sun. Because there's this big difference in the amount of heat gained from the sun, from the equator to the poles, the equator actually has a sort of overall surplus of heat energy, and the poles are losing more heat energy than they're gaining. Uh, Overall, planet Earth is in thermal equilibrium, which means its temperature is relatively constant. It's losing the same amount of heat through radiation of heat to space as it is gaining in terms of solar heat from the sun. So its overall average temperature is not changing, but there are differences between latitudes because the individual latitudes of the Earth are not in thermal equilibrium. There's this sort of net heat gain in the lower latitudes and net heat loss in the upper latitudes. And that means that there has to be a heat transfer from the lower latitudes where there's a surplus of heat gained to the higher latitudes. And that heat transfer is um, accomplished through atmospheric circulation, both the circulation of air masses, which transfer about 1/3 of the heat from low latitudes to higher latitudes, and ocean currents. Sorry, the air masses transfer about 2/3 of the heat energy surplus of the low latitudes to the high latitudes, and ocean currents transfer the remaining 1/3 of heat energy from the low latitudes to the high latitudes. So you can kind of think of the entire ocean atmosphere system of the Earth as like a giant version of that room with the radiator. And the equator is sort of where you've got that excess heat and the rising air. And that rising air will then sort of flow across the upper atmosphere towards the pole. Then it will be cooled and sink and slide back towards the equator along the floor or the surface of the Earth. And you get this sort of circulation cell of air rising at the equator, spreading out across the upper atmosphere, and descending at higher latitudes and sliding back towards the equator to be warmed and rise again. So the real situation is more complicated than this, but this is the basic principle of convection that drives the winds of planet Earth. Some of the things that make reality more complex than that simple diagram are the fact that Earth is really large, and the air has time to sort of go through not just one big circulation cell from the equator to the pole, but multiple cycles of rising and falling. And they call each of these sort of rising and cycles of rising and falling a circulation cell. And there's sort of three basic bands of circulation cells in each hemisphere of the Earth. The northern hemisphere and the southern hemisphere is sort of the mirror image of the northern hemisphere. So we'll just describe them for one hemisphere, and you can sort of understand that they are repeated in the other hemisphere. So if this is the Earth here, this is not the roundest Earth that's ever been drawn, but that's the equator. The Hadley cell is the circulation cell that forms from the equator to about 30 degrees latitude. The Ferrel cell is the cell of circulation from 30 degrees to 60 degrees latitude, and the polar cell is the cell of circulation from 60 degrees latitude to the pole, 90 degrees latitude. And so that would sort of result in sort of equatorward surface winds from 30 degrees latitude to the equator, poleward surface winds from 30 to 60 degrees latitude, and equatorward surface winds from the equator to from the North Pole or South Pole to 60 degrees latitude. It's still more complicated than that, though, because there's this something called the Coriolis force, which is related to the Earth's roundness and rotation, that seems to bend the wind. So instead of just getting these sort of north-south flows of surface winds, we get something a little more complicated than that. This diagram here is more nicely drawn than the one that I just drew on the last slide, but it shows the same latitudinal bands of the Earth, basically 0 to 30 degrees, corresponding with a Hadley cell of atmospheric circulation, 30 to 60 degrees, corresponding with a Ferrel cell of atmospheric circulation, and 60 to 90 degrees, corresponding with a polar cell of atmospheric circulation. So what we expect is that in the Hadley cells, we would get this sort of equatorward flow of wind, where the rising wind at the rising air at the equator, descending air at 30 degrees latitude, rising air again at 60 degrees latitude, descending air over the poles, and these sort of corresponding wind directions related to that at the surface. Okay, so in general that is the case, but these winds that sort of flow towards or away from the equator are acted upon by the Coriolis effect, which deflects the winds for reasons that we'll talk about in the coming slides. In the northern hemisphere, winds are deflected to the right of their initial direction, and in the southern hemisphere, winds are deflected to the left of their initial direction of motion. So the result that you get from the sort of equatorward or poleward flow then being deflected by the Coriolis effect are these bands of winds on the different latitudinal zones of the Earth that have distinctive names. So the bands of wind from the equator to 30 degrees latitude are called the trade winds. And in the northern hemisphere, they're called the northeast trades because they come mainly from the northeast. In the southern hemisphere, they're called the southeast trades because they come mainly from the southeast. So you can see that sort of combination of equatorward and flow and the eastward deflection, or sorry, the deflection towards the west. Winds are actually named for the direction that they're coming from, not the direction that they're going to. So the westerly winds in the higher latitudes are winds that are coming from the west and flowing eastward. And the polar easterlies are winds that come from the east from around the poles. So the three main latitudinal bands of wind that you need to know are the trade winds, the westerlies, and the polar easterlies. And we'll also talk about some special transition zones between the wind bands, such as the horse latitudes around 30 degrees from the equator and the doldrums right on the equator itself. So let's dig more into this force that mysteriously deflects the winds from their initial direction of motion. This Coriolis effect is a complex effect, and it's driven by the fact that the Earth is a sphere and it's rotating. If you have trouble remembering which direction the Earth is rotating, think about which coast gets the sunrise first. So, if this is the Earth, and I'm going to very badly draw the United States here on the Earth. Um, it's Maine. The East Coast gets the sunrise first, and the West Coast gets the sunrise second. So that means if the sun's out here in space, the direction of Earth's rotation must be like this. If the East Coast sees the sunshine first before the West Coast does. If you're looking down from the North Pole, this rotation would be a counterclockwise rotation of the Earth. So that's the direction that the Earth is rotating, if you ever forget. The Coriolis effect, what it does is it causes any object in motion to seem to deviate from its original course. Objects in the northern hemisphere will deviate to the right of their initial direction of motion, and objects in the southern hemisphere will deviate to the left of their original direction of motion. If you're right on the equator, there's no Coriolis force. So this diagram shows the Coriolis deflection at various points on the Earth. So the dotted arrows are the intended path of the object. Like if you threw a ball or shot a bullet, that would be the direction that you threw it or shot it in. And then the curved paths are where it actually ends up going because of the Coriolis deflection. So you can see in the northern hemisphere, things are always going off to the right of where they were initially shot or thrown, and in the southern hemisphere, they're going to the left of that. As an example, you can use a jet plane, right? So if a jet plane was leaving Sweden, Stockholm, Sweden, and trying to fly to Lagos in Africa, it might sort of take off and head straight that way, but its actual flight path, if it didn't make any steering corrections, would take it instead to South America. And that is because the rotational velocity of the Earth towards the equator is much faster than at the pole. So basically, it's like the Earth is spinning underneath the flight of the plane faster than the plane's initial motion was when it took off in Stockholm. So it's kind of like you can imagine the Earth sliding around underneath as the plane was flying south, therefore causing the plane to land in a different place. Because the Coriolis effect is pretty tricky to visualize, animations help a lot. And in this lecture, which I've made available on the course page for FGCU Oceanography, you can click on these links to take you to Coriolis force explanation from the United Kingdom's Meteorological Office. And there's another video explanation that uses a spinning merry-go-round to sort of demonstrate the Coriolis effect on a small scale. Okay, so Coriolis effect, it's a tricky thing, but if you just remember that shorthand of the rightward deflection in the northern hemisphere and the leftward deflection in the southern hemisphere, you'll probably be okay. But you'll still want to watch those videos for the explanation of the mechanism behind it. Now, we're going to get into giving a lot of detailed explanation of wind. Before we do that, we should make sure we've got our wind terminology straight. So winds are named not for the direction they're going, but for the direction that they're coming from. And that's probably because the direction that the wind is coming from is more relevant to the type of weather that it brings. For example, a north wind is wind that comes from the north, bringing with it cold air if you're in the northern hemisphere. A south wind is wind that comes from the south, bringing with it sort of typically warm, moist air from the tropics if you're in the northern hemisphere. Likewise, an east wind comes from the east, and a west wind comes from the west. Somewhat confusingly, ocean currents are not named for where they're coming from. Ocean currents are named for where they're headed. So the Gulf Stream, for example, which flows from the south, is called a northward current. Okay, this little slide here is reviewing the names of the sort of latitudinal bands of different wind conditions on Earth from the equator to the poles. So first we've got the types of winds that we have around the equator, which are called the doldrums. Around the equator, the winds are usually light and variable. This is a place where, because the equator is receiving so much solar heating, air is warmed and rises. So there's sort of a rising motion of air and not really a horizontal movement of air so much. So the winds are sort of light and variable. There are a lot of thunderstorms, and it's a tough place to sail through because it's hard to catch a good wind, and you may find yourself just dealing with a lot of hot, sticky air and thunderstorms, and it could be depressing too. So think about sort of hot, sticky, light winds. Those are the doldrums. That's the type of wind pattern you have around the equator. When you get a little bit further from the equator, up to about 30 degrees north latitude, you're in a really nice wind zone that sailors like. They call it the trade winds. And the winds come from the east in the trade winds, and that's sort of the surface flow associated with the Hadley circulation cells of the atmosphere. The It's really easy to cross the Atlantic Ocean in the trade wind zone if you're at a latitude between 30 degrees and the equator, because you can just sort of put your sails up and point your boat towards from Europe to North America, and you just whisk away right there. It's a little trickier to return, but if you wanted to make a return voyage, you'd probably go to a higher latitude and catch the westerlies, which could blow your boat from North America back to Europe. But you'd have to first uh, drive your boat north along the coast until you got into that latitudinal wind band to make your return voyage. Between the trade winds and the westerly winds, there's sort of this zone of um, sinking air. It's a high pressure zone, and there tend to be light and variable winds there. So just like there's a zone of light and variable winds at the equator, that due to rising air, there's a zone of light and variable winds around 30 degrees latitude due to sinking air. They call it the horse latitudes because sailors would sometimes get stuck in the horse latitudes and not be able to sail out of them for a long time, and they would have to get rid of their excess cargo, including, sadly, their horses would sometimes have to get thrown overboard because the horses require a lot of food and water to maintain. So um, that kind of thing doesn't happen so much anymore, but it's just one of the gruesome parts of history. I should mention the westerly winds in mid latitudes of the Earth from 30 to 60 degrees away from the equator are associated with the Ferrel cells, the mid latitude circulation cells. And the highest latitude wind bands on Earth are called the polar easterlies. Those are winds that flow from the east, and that is sort of high pressure air sort of that descends at the pole and flows south and east uh, until it's warmed and can rise again. So this diagram here you've seen before, but I've just sort of highlighted the names of all the wind zones that you'll need to know for this class. Both the bands of good wind, the polar easterlies, prevailing westerlies, and trade winds, and then the bands of bad winds, the horse latitudes and the doldrums, which are at the uh, descending and diverging winds for the horse latitudes, and the converging and ascending winds for the doldrums. This graph here is just sort of another visualization of the same kind of thing we saw in the last diagram. And I like this visualization because it shows both the circulation and the Coriolis deflection that you get with this global wind pattern. You can also see the differences in flow direction that you have at the surface, which are sort of the orange arrows here. These are the surface winds, the ones that you'd feel as a sailor or someone walking across the land. And then the high altitude winds, which you see on the top of the diagram here, those are the winds that are sort of at the upper atmosphere, sort of completing that circulation of that atmospheric circulation cell. Another thing you can see in this diagram here is that the atmosphere is actually thicker at the equator than it is at the poles. And that's because the polar air is colder and higher density. So the atmosphere is actually thinner, more compact at the pole than it is at the equator. The atmosphere is actually thicker. One great way to see the real winds of Earth, because of course, winds are usually invisible unless there's a lot of dust or leaves in the wind, is to look at real-time models of Earth's wind. And earth.nullschool.net is a sort of Google Earth type online tool where you can play with this animated model of Earth's winds and see for the present time which directions the winds are flowing in different parts of the world and how strong they are. The color coding here is how strong the winds are. So you can see that there's a few places in the Atlantic Ocean, for example, where there are strong circular winds related to hurricanes. We're actually really worried about this one here, Hurricane Milton, affecting Florida in a couple days. Now we're going to talk a little bit about the difference between weather and climate. And we're going to say a few things related to atmospheric circulation in terms of climate and a few things, more things related to weather. So weather is sort of like the short-term immediate conditions in the atmosphere. So that's like today, yesterday, tomorrow, next week. When you go to a weather forecasting site and see a graph like this of the multi-day forecast, that's weather that we're talking about. And climate is more of like the long-term patterns of conditions. So on average, what are the average temperatures of this area? What are the record highs and lows? What's the typical seasonal pattern? So climate is sort of larger scale and longer time scale patterns in weather. So weather is sort of right now, it's highly variable. Climate is sort of zooming out and looking more at the big picture of what the weather is like over long term. And we can really zoom out to very long-term climate analyses for planet Earth because even before people started keeping track of weather and writing down temperatures in books and computers, Earth recorded its temperature in various ways in terms of chemical composition of ice and sediments. And geologists and paleontologists have been able to analyze these so-called paleoclimate proxies to figure out what the climate conditions were like in the ancient past of Earth before there was conventional weather forecasting, before there were even humans. And this image here shows the past climate of the Earth going back 550 million years. And it's broken up into different time scales. So for the last 20,000 years, we have sort of a zoomed in view. For the last 1 million years, it's a little more zoomed out. For the last 5 million years, it's more zoomed out than that. For the last 65 million years, it's even more zoomed out. And then for the last 500 million years, it's the most zoomed out. So the time is sort of compressed as we go back further, and we're more zoomed in as we go up further in this diagram. And what you can see is that the climate of the Earth has varied in interesting ways over both the very long term and the shorter term history of the Earth. One of the most significant recent changes in climate, recent meaning in the last 20,000 years, has been the sort of our thawing out from the last glacial maximum. So global temperatures were about 5 degrees Celsius colder during the last glacial maximum about 20,000 years ago, and they warmed up a lot to basically their modern temperatures by about 12,000 years ago. And from 12,000 years ago until the present time, we've had sort of relatively steady temperatures, varying sort of less than a degree on the global average terms. But it's kind of hard to see right at the most recent modern times, we're jumping up in temperature again due to anthropogenic global warming. So we're really having sort of a sudden break from the relatively steady long-term climate that we've enjoyed for the last 12,000 years, and that's because of human effects on climate. The human effects on climate that we're experiencing today are based on something that's actually a natural part of Earth's climate system, which is called the greenhouse effect. So the greenhouse effect is the property of the Earth's atmosphere that causes it to retain heat. Basically, the Earth receives radiative heat from the sun in the form of solar radiations, and some of that heat radiates back into space, which is why the Earth doesn't just keep getting hotter and hotter forever. But some of the heat is sort of absorbed in the atmosphere and then radiated back to Earth. So Earth's atmosphere kind of functions like a blanket, allowing the Earth to build up a little more heat than it would otherwise. So the Earth's actually warmer because of its atmosphere than it would be without the atmosphere. And certain gases in the atmosphere help it retain heat. Um, and so what's happening now is that human activities are increasing the concentration of some of those gases in the atmosphere, causing the blanket effect of the Earth's atmosphere to be stronger. So basically, the Earth is retaining more of the sun's heat than it used to, and that's what's causing that recent dramatic warming that we're seeing on Earth. And the gas in the atmosphere that is most affected by human activity and most responsible for the recent warming that we're seeing is carbon dioxide gas, CO2. So it's the concentration of carbon dioxide gas for the last um, you know, 12,000 plus years has been about 280 parts per million. But because of human activities like fossil fuel burning and cutting down forests, we've released a lot of extra carbon dioxide in the atmosphere, and the concentration is now over 400 parts per million. So that's a big increase from 280 parts per million. In fact, at this website here, you can find the most recent carbon dioxide concentrations in the atmospheres from the Mauna Loa Observatory on top of a mountain in Hawaii, where they've been recording atmospheric carbon dioxide concentrations for a long time and noticing this like really serious increase in carbon dioxide. Um, the graph here shows a record that goes back before that Hawaiian mountaintop observatory was formed, because we have other records of carbon dioxide concentration from earlier times. So basically, we put this whole record together. We see this pattern that looks kind of like a steady state that up until about 1850, which is when human population growth and industrial activity really took off and started producing CO2, contaminating the atmosphere with this excess of CO2, which is enhancing the greenhouse effect and causing the climate to warm. This graph here, I'm sorry for the sort of the poor color font choice for this atmospheric thermal equilibrium diagram here, is just sort of a more detailed and technical diagram of sort of Earth's atmospheric and planetary heat budget. Basically, we've got incoming heat from the sun, and some of that is reflected back into space. Some of that's absorbed by various elements of the atmosphere, ocean, and land. And some heat, of course, is radiated back into space, and that's why Earth is normally in a pretty steady state in terms of temperature. The part of this diagram that involves global warming is this absorption of heat that would otherwise escape the Earth by greenhouse gases like water vapor and CO2. So this sort of blockage of the escaping heat from Earth by greenhouse gases is something that's happening more so now that we've got an increasing concentration of CO2 and other greenhouse gases in the atmosphere, and that's what's causing the global mean temperature, the global average temperature to increase. All right, so we're going to put climate on the back burner for a little while to talk more about weather. So there's some basic concepts of weather that we're going to learn here. We're going to learn more about isobars, which we already talked a little bit about, and their relation to pressure systems. We're going to talk about jet streams. We're going to talk about fronts. We're going to talk about certain types of wind called sea and land breezes. And we're going to finally talk about tropical cyclones, which include hurricanes. So first off, isobars. We mentioned earlier, isobars are lines of equal atmospheric pressure. Iso means the same, and bar is a term for pressure. So lines of equal atmospheric pressure. In this diagram, there's also some color coding added so that the high pressure is sort of warm colors and the low pressure is cool colors in this diagram. These aren't necessarily associated with temperature differences, but just to help you visualize the pressure, they've got some colors along with the numbers here. And these pressures are expressed in millibars. So you'd say that this pressure here is 1,000 millibars pressure. The letter abbreviations L and H are typically used for low pressure and high pressure areas. And so when you're looking at one of these weather maps that has a top-down view, you'll often see what looks kind of like a rough bullseye with an H in it, if that is what they call a high pressure center. So a high pressure center is where it's sort of like the highest pressure in the area surrounded by lower pressure air. So people observers on the ground sort of can measure air pressure with instruments like a barometer, and they put together all those measurements and connect the dots to form these sort of maps of where the high pressure or low pressure areas are. And we're going to look at this high pressure area and in more detail and try to kind of understand how air would flow and how winds would develop around this high pressure area. So because high pressure air is higher pressure, it will tend to sort of flow outward from the high pressure center towards lower pressure areas surrounding it. So the tendency will be for this sort of divergence of air from the high pressure center to the surrounding area. So air is going to want to spread out from the high pressure center. However, Coriolis effect is a thing. So you're not going to get sort of straight wind flow directly out from the high pressure center. The wind is going to be acted on by the Coriolis force, which in the northern hemisphere will deflect the flow to the right, in the southern hemisphere would deflect to the left. But this forms this sort of rotating winds around the high pressure center. And in the northern hemisphere, that rotation is clockwise. And this type of rotational winds that develop around a high pressure system are called an anticyclone. So in the northern hemisphere, an anticyclone is a clockwise rotation. In the southern hemisphere, an anticyclone would be a counterclockwise rotation. Now, low pressure systems also are associated with particular wind patterns. Low pressure is where the pressure is lower than the surrounding air, and the tendency will be for air to flow inward towards the low pressure center. They call that convergence. But of course, Coriolis forces act on the air as it flows towards the low pressure area, and in the northern hemisphere the Coriolis force will deflect those winds to the right, so you'll get this sort of overall counterclockwise flow of air around the low pressure center, and that in the northern hemisphere and the southern hemisphere it would be clockwise, and that flow of air around a low pressure center is called a cyclone. we're going to look at the isobars and the wind flow around an actual cyclone. This is Hurricane Milton, which is currently in the Gulf of Mexico near the Yucatan Peninsula. And in this diagram here, the yellow-green colors are higher pressure areas. So there's sort of higher pressure areas on the periphery of this cyclone, and there's a low pressure area at the center of the cyclone with lower pressures there. So you'd expect the winds to flow from the high pressure to the low pressure area, but of course the winds get deflected by the Coriolis effect to the right of their initial direction of motion. So I think what we're actually going to get is sort of a counterclockwise spiraling flow. And from the same weather forecasting service that I downloaded this photo from, there's a map of the actual wind field for this system. And that does indeed show a counterclockwise wind flow around Hurricane Milton. So this is always the pattern of flow around hurricanes, which are low pressure systems in the northern hemisphere. They always flow counterclockwise, and the southern hemisphere would be clockwise. So in general, high pressure centers which are associated with sinking air, and low pressure centers are associated with rising air. High pressure centers have this diverging air at the surface. Basically, it flows outward from the high pressure center, and then it's affected by Coriolis force, causing anticyclonic rotation. So this would be anticyclonic, and a low pressure system where there's converging air flowing towards the low pressure would be a cyclonic rotation. And I just want to show this extra diagram here because it shows the sort of three-dimensional aspect to this. It's not just, the atmosphere is not just a 2D sheet around the Earth. There's actually sort of rising and falling in addition to sort of the east-west, north-south movements of air in the atmosphere. So there are these sort of typical zones on the Earth where we normally have high pressure or low pressure air because of the differential heating and cooling of different parts of the Earth and the atmospheric circulation cells that generates. So these areas are not perfectly aligned with the 0, 30, and 60-degree latitude zones that we talked about earlier, where we had this really tidy, like trade wind zone, westerly zones, polar easterly zone. The reality is a little more wiggly, and that's because there are some interfering effects of continents and oceans. Continents can warm up faster and cool down faster than oceans because water has a sort of a high heat capacity. It holds a lot of heat, but it takes a long time to warm up, whereas land is not like that. And also, the locations of high and low pressure areas change with the seasons as the northern hemisphere and the southern hemisphere are sort of alternating, which is receiving more solar radiation. So we can see in the northern winter, which is the upper graph here, you've got this sort of different locations of the high pressure areas and low pressure areas, and in the summer, in the northern hemisphere summer, that shifts. One of the things that you can see changing a lot is the location of this blue line that runs roughly around the equator. That blue line is called the Intertropical Convergence Zone, abbreviated ITCZ. And the Intertropical Convergence Zone is synonymous with the doldrums. So that's the area of sort of low pressure rising air that's roughly around the equator, but not always exactly at the equator. And you can see that basically in the northern hemisphere's winter, the sort of equatorial zone is further south, and in the northern hemisphere summer, this intertropical convergence zone is further north. and that strongly affects weather. So in this diagram here, you see sort of the typical wind directions on the Earth, which again is a lot messier than that simple conceptual diagram that we looked at a few slides back. But it does show some of the general patterns that we talked about, like the trade winds that flow from east to west in the tropical latitudes. But it shows that there's a lot of variation in those wind patterns. There's the westerly winds in the mid latitudes, but there is a lot of sort of variation from place to place and variation from season to season in the wind patterns. For example, you get this sort of flow off the Asian continent towards the Indian Ocean in the northern winter, and you get this flow from the Indian Ocean onto the Asian continent in the northern hemisphere summer, for example. One of the So some of these like persistent high pressure areas or persistent low pressure areas have names, and meteorologists will sort of refer to those sort of persistent high or low pressure areas by their names, and in order to sort of discuss the influence that these persistent high or low pressure areas have on weather patterns. And in our region of the world, the sort of Atlantic coast of the United States, our weather patterns are strongly affected by this high pressure system over the subtropical latitudes of the Atlantic Ocean, which is called the Bermuda Azores High. So the Bermuda Azores High is really important for steering hurricanes and other weather systems that affect the U.S. So the position of the high is such that it kind of causes this uh, clockwise rotation around it. And if there's a hurricane out in the Atlantic, it will sort of often get deflected on a path northward and hopefully away from the U.S. coast by the Azores High. But if the Azores High is in a little different position, more over Bermuda, then the hurricane might not get deflected north and might end up impacting areas further westward, like Florida. Another important weather phenomenon or aspect of Earth's atmospheric circulation that we need to discuss are jet streams. So jet streams are associated with the sort of upper atmosphere part of the atmospheric circulation cells. They're high altitude winds, so we don't feel the jet streams at the surface, but the jet streams can affect the position of air masses on the Earth and indirectly affect surface weather. Um, and okay, my phone is sending off an emergency alert for Hurricane Milton, so this is high stakes here. All right, there's multiple jet streams on Earth, but the two major jet streams are the subtropical jet, which is about 30 degrees from the equator, where there's sort of sinking air. This is sort of the edge of the Hadley cell where there's convergence and air begins to sink. There's sort of an acceleration of winds at that level in the upper atmosphere where that process starts to happen, and there tends to be sort of strong wind flow in that area. And then there's the polar jet, which is where there's associated with rising air at around 60 degrees north at the boundary between the polar cell and the Ferrel cell. And this is a side view, obviously, in this diagram, but if we look at sort of a top view of the winds associated with the jet stream, we can see more or less where they are. Also, you can see that the jet stream is not like a nice straight line. The jet stream tends to meander a lot. It has sort of a wavy appearance. And those waves in the jet stream have a strong influence on weather. Where there's a dip downward in the jet stream, you can get cold air being brought down from the north. Where there's a dip up in the jet stream, you can get warm air brought up from the south. So the jet streams, particularly the polar jet, have a strong influence on weather. This video linked here from the United Kingdom's Meteorological Office has a really cool explanation of jet streams and talks about what they are in general and also their influence on the weather of Britain. Okay, the next weather phenomenon or weather feature that is we're going to discuss here are fronts. Usually the word front is preceded by cold front or warm front. So fronts are basically boundaries separating air masses with different characteristics. So it could be the boundary separating a cold air mass from a warm air mass. That's the type of thing that you would call a front. Um, and fronts are illustrated on weather maps with blue, red, or purple lines. And so like this line here is a cold front, this line here is a warm front, and this line here is a special mixed kind of front called a occluded front. So we're going to learn more about these types of boundaries between warm and cold air masses on the next slide. So um, cold fronts, those are illustrated by a blue line with triangles on it on weather maps, and generally they move from west to east. And where a cold front is approaching, oftentimes there'll be showery precipitation like thunderstorms with dramatic cumulonimbus clouds. Warm fronts, they move poleward. So like in the northern hemisphere, they're associated with south winds, winds coming from the south. They're indicated by a red line with half circles on it on a weather map. And as a warm front is approaching, usually you get sort of stratus clouds, so it'll be overcast or foggy, and there might be a little gentle precipitation associated with a warm front. Occluded fronts are sort of a combination of warm and cold fronts, where warm and cold fronts are interacting and combining. And so they're indicated by a mixture of triangle and half circle symbols on a purple line. And then stationary fronts are where there is sort of a warm and cold air mass that are sitting next to each other, but they're sort of at a stable standoff. One's not moving into the other. They're just stationary. So a lot of interesting drama happens when a warm front and a cold front meet. And in this diagram here, there's a warm front coming up from the south over the Gulf of Mexico, meeting a cold front coming from the western United States and Canada. And at the interaction, because the cold air is more dense than the warm air, you see the warm air rises over the cold air mass. And where that happens, the moisture that's contained in that warm air condenses, forms into clouds and precipitation. And in this sort of more side view image, you can see some of the general types of weather that you get along fronts. So where a cold front meets warm air, you tend to get this dramatic precipitation of cumulonimbus clouds and showery precipitation. Where a warm front rises over cold air, you get more sort of gentle overcast conditions and more diffuse precipitation. Warm fronts generally have sort of wider boundaries versus cold fronts that have sharper, narrower boundaries. So cold fronts have sort of brief, dramatic precipitation, and warm fronts have more spread out, longer precipitation. There's this sort of weird type of mixed front where a cold front is sort of catching up with a warm front. So the warm front's coming up from the south, the cold front's coming in from the west. And when the cold front kind of overlaps or catches up with a warm front, you get this type of special front called an occluded front. Basically, the cold air wedges under the warm air, and the front gets kind of pushed into the higher atmosphere. So occluded fronts can lead to sort of like a lot of precipitation over a long period of time. And occluded fronts are one of the features that develops where there's a sort of a dancing interaction between the polar cell and the feral cell, where the relatively warm air mass of the feral cell interacts with the colder air of the polar cell. So um, this is a little sequence of diagrams from the upper left, then it's sort of moving forward in time and sort of tracking the development of this interaction between the warm air mass and cold air mass at the frontal boundary between the polar cell and the feral cell. So this boundary is often not stable. Waves will sort of develop along this boundary due to the meanders in the jet streams and other factors. And that can cause this sort of rotation, which results in moving fronts. So you get the cold front moving in from the west, the warm front moving up from the south, and that sort of generates this rotation that eventually leads to an occluded front and this sort of spiraling storm around the a low pressure area associated with the occluded front, and that generates a lot of wind and precipitation. And because it has a rotation to it, it's called an extratropical cyclone. So one type of extratropical cyclone that has a colloquial name, nor'easter, is common in the northeastern United States, where cold fronts from the west will sort of sweep down from the Great Lakes area and interact with warm fronts coming up along the Atlantic coast and generate that type of interaction that at the surface leads to strong winds from the northeast that can cause coastal flooding in the New England states and can cause really rough and dangerous sea conditions in the North Atlantic. So the typical time for nor'easters to occur is the fall, so late October and November. There's a lot of rapid weather change. Because landmass has cooled down, it's starting to get really cold over Canada in the fall, but it's still warm over the Atlantic because of the high heat capacity of water and the role of the Gulf Stream bringing warm water northward in the Atlantic Ocean. Sometimes there's hurricanes that are bringing really warm, humid air masses up along the Atlantic coast as well, and those hurricanes can interact with the cold air masses coming down from the Arctic and Canada and cause a really violent weather interaction called the nor'easter. One of the worst nor'easters ever was sort of an interaction between a hurricane and a powerful cold front that developed off of New England in 1991, and it was called the perfect storm. It was such a terrible storm that it caused a lot of coastal destruction, and it also caused loss of life for the fishing crew of this swordfish longlining boat, the Andrea Gale. And so the uh, fishermen who lost their lives on that boat, their story was written up in a book called The Perfect Storm, and then that actually became a popular movie starring the actors George Clooney and Mark Wahlberg. So um, hopefully, weather forecasting is a little better than it was back then, but still sometimes sailors can find themselves caught in the wrong place, and that certainly was the case for the crew of the Andrea Gale, who all perished in the perfect storm. So some things that you should think about as we're kind of reviewing what we've learned so far are listed on this slide here. Which type of fronts have the widest boundaries? Your options are cold front, warm front, occluded front. The answer to that one is warm fronts. Warm fronts, the warm air will sort of gradually rise over the colder air mass that it's overtaking, and so the warm fronts tend to have wider boundaries. The type of front that's signified by a purple band is the occluded front. The general name for the air rotation pattern around a high pressure zone is, let's see, anticyclonic rotation. And the actual direction of that rotation in the northern hemisphere would be clockwise. In the southern hemisphere, let's draw the equator there. In the southern hemisphere, that rotation would be counterclockwise, but you would call them both anticyclonic rotation. Um, the name of the local high pressure zone in the subtropical Atlantic Ocean is the Bermuda Azores High. Sometimes people just call it the Bermuda High, but Bermuda Azores High is the name for it. And what direction does a cyclone rotate in the northern hemisphere? Well, remember that a cyclone is a low pressure system, so air is going to want to flow towards the low pressure system. But because of the Coriolis deflection, the air ends up flowing to the right of its intended direction of motion, and that is going to generate a counterclockwise flow of air around the low pressure system in the northern hemisphere. Okay, moving on to a sort of more nuances of winds. One type of wind pattern that can generate where the land meets the sea is referred to as a sea breeze, and then there's sort of a corresponding breeze called a land breeze. And these sort of winds that happen along the coast are driven by air temperature and pressure differences that occur over the land versus sea due to their differences in heat capacity. Basically, land warms up faster than the ocean, and so the warmer land transfers its heat energy to the air above it, causing warming rising air over the land during the day. And that warming rising air over the land creates a low pressure area, and then the relatively more dense air over the cooler ocean will sort of flow landward towards this rising air over the land, causing what's called a sea breeze. So sea breezes, they develop during the day. Oftentimes they're strongest in the late afternoon. And then what's interesting is that in some of those same areas that have sea breezes during the day, they can have land breezes at night. So the land will cool off, causing air to descend over the land, whereas and sort of flow. That descending air will flow towards the ocean, where it actually warms up because the ocean still has retained its heat from the day, and you get this sort of rising air over the ocean at night, and what they call an offshore flow, meaning like flow from the land to the sea at night. So those are sea breezes and land breezes. And those are connected with this phenomenon called monsoons. Monsoons are like sea breezes on steroids. So um, they're basically this continental scale sea breeze. And the most famous monsoons are the ones over South Asia and the Indian Ocean. So there's a very different kind of weather condition in the winter versus the summer in the around India. So India is this subcontinent here in the diagrams. Um, so when it's wintertime, there's sort of high pressure over the cold landmass of Asia and sort of falling air that flows equatorward towards the intertropical convergence zone. And the intertropical convergence zone is pretty far south in the southern hemisphere, usually in the northern hemisphere's winter. During the northern hemisphere summer, the landmass of Asia heats up a lot and actually gets very hot in South Asia, hotter even than the warm Indian Ocean. And that causes rising air over the land and a shift in the intertropical convergence zone northward, which sort of brings lots of convective moisture from the Indian Ocean onto the continent of India and South Asia, and so they get a lot of rain in summertime. The link, which you can find in the PowerPoint that's been uploaded to Canvas, will go to one of those United Kingdom Meteorological Office video explanations of the monsoon. Now we're at our sort of final weather topic. Tropical cyclones. Tropical cyclones is a general term that includes hurricanes, typhoons, and cyclones, which are all basically the same thing. They just have different names in different parts of the ocean. But these are highly powerful, highly consequential weather systems that develop in certain parts of the world and can be really destructive. I personally had my house flooded by Hurricane Ian in 2022, and I had to leave and move to a new place. So these can be really disruptive to our lives, and it can even cause death and destruction. So it's important to learn about these things so that we can stay out of their way and understand and predict them better. So the tropical cyclones are powered basically by the stored heat energy in warm ocean waters. And through various mechanisms, that heat energy is transferred into kinetic energy of the atmosphere and sort of the motion of the air mass. So this formation of these large storm systems is actually part of that transfer of the excess heat that the low latitudes of Earth absorb to the higher latitudes where the heat is radiated away into space. So they're sort of important in terms of the global climate regulation, but that's of little consolation to the people that are affected by their destruction. Looking sort of at global surface water temperatures can give you an idea of where hurricanes are likely to form. This is color-coded diagram shows average surface temperatures of the world's oceans, and you can see that there are hotter areas around the equator in most of the world, which are where the hurricanes tend to develop. Interestingly, some parts of the world's oceans, even though they're near the equator, are relatively cool, and hurricanes are actually absent from those areas. The wind patterns in a hurricane are basically rising air. So there are low pressure systems at the center where air rises. When air reaches the upper atmosphere, then it diverges and spreads out away from the eye of the storm. So at the surface, wind is sort of flowing in towards the storm, collecting that energy from all the warm ocean. It rises, and then at the top, it spirals outwards. The center of the hurricane is this unusual feature called the eye, which is where it's paradoxically clear. It's not cloudy. And sometimes in these satellite or space station pictures of hurricanes, you can actually see the blue surface of the ocean in the center of the eye, where it's cloudless. It's relatively calm. There's sinking air and light winds. But of course, in the periphery of the eye, the winds are very, very strong and destructive. There are some other features in the hurricanes called spiral rain bands, which are these sort of bands of intense thunderstorms that wrap around the hurricane. So in the tall clouds and the spiral rain bands, there are towering thunderstorms. And then in between those bands, there are smaller areas of sinking air that then is warmed again and flows back towards the center of the hurricane. So hurricanes have this kind of complex structure of bands of rising and sinking air rotating around the low pressure area at the surface at the bottom of the storm. This 3D computer generated graph here shows something that's interesting about storms, which is the cyclonic rotation of the surface level winds. And in the northern hemisphere, that's a counterclockwise rotation, whereas the upper level winds, where they're diverging away from the eye of the storm at the cloud tops, are actually flowing in the other direction. That's a sort of a high pressure divergence, which creates this anticyclonic clockwise rotation at the upper level of the storm. And sometimes if you're looking at animated satellite photos of a storm, you can see both of those types of overlapping circulation in the storm. Hurricanes don't form in all parts of the world, but they form basically wherever the water of the tropics is warm enough. And they go by different names in different parts of the world. In the coasts of the Americas, of North America and the Northern Hemisphere, they're called hurricanes. So in the Eastern Pacific and in the Atlantic Ocean, they're called hurricanes. In the Western Pacific, they're called typhoons. In the Indian Ocean and the South Pacific Ocean, they're called cyclones. Hurricanes are rare in the South Atlantic Ocean, but they do occasionally form, and they are called hurricanes there. And then the part of the world where they don't form is the Eastern South Pacific. And the reason they don't form there is because there's a lot of cold water upwelling there that prevents hurricanes from forming there. There are other interesting weather and atmospheric phenomena that do happen there, like the El Nino La Nina cycles happen in this area. But because it's cold, there's a lot of upwelling there. We've never, at least so far, had a hurricane in this part of the world. So how does the hurricane actually form? It's a process with a couple of steps. Various things have to come together for a hurricane to form. One is that you have to have high water temperature and with high ocean heat content. So typically the water has to be at least 20 degrees Celsius, and that warm water has to not just be a thin layer on the surface, but has to extend down to about 60 meters deep. Because as the hurricane starts to develop, it'll use up the heat from the surface layers of the ocean, and it'll have to draw on heat from deeper water that gets mixed up by the waves of the hurricane. So basically, the hotter the surface water is and the thicker that slab of hot water is, the more ocean heat content there is to fuel the hurricane. Latent heat is released as condensation when sort of the warm surface air above the oceans rises. There's condensation, and that process releases heat from the water. That's one of the ways that heat is transferred from the tropical waters and the surface of the Earth to the upper atmosphere and higher latitudes. Rising air is powered by that latent heat. So as condensation happens, that warms the air, and that allows further rising of the air. That's how you get the sort of the towering cloud tops of the hurricane. And if this is just happening in one spot, all you get is a thunderstorm. But when you get this sort of converging weather systems, like a network of thunderstorms that all sort of come together and combine, that's when you can start getting this sort of self-sustaining, really powerful system that we call a hurricane. And there needs to be some rotation to bring those thunderstorms together. So you don't get the formation of hurricanes right on the equator because the Coriolis force is weak to non-existent right at the equator. But when you're a bit away from the equator, the Coriolis force is stronger, and that can provide the sort of rotational velocity around the low pressure centers of thunderstorms that allows them to sort of combine and form a hurricane. The other thing that you need to sustain the hurricane is a lack of wind shear. Wind shear is where wind at different levels in the atmosphere, like if this is the ocean surface, if the wind on the ground level is going this way and the wind at different levels in the atmosphere is going different directions, that can sort of break up the hurricane. Whereas if the winds are all synchronized at different levels in the atmosphere, then the hurricane will not be disrupted by wind shear, and it can organize itself into a more powerful storm. Hurricanes are incredibly destructive, as we Florida residents know. One of the things that's most destructive about the hurricane is not only its strong winds, but it's what we call the storm surge. So the low atmospheric pressure at the center of the storm can actually cause the sea surface to be elevated relative to the surrounding ocean. So that pressure difference alone can cause rising sea level. But what really makes the storm surges tower is the waves driven by the strong winds of the storm, which pile up along coastlines and can cause really, really high waves and water levels that inundate coastlines. That tends to be the most deadly aspect of storms, although another catastrophic aspect of storms is the extreme precipitation that they bring as this sort of giant mass of tropical moisture derived from the warm tropical waters is sort of cooled in the upper atmosphere or higher latitudes, causing tremendous precipitation that can cause flooding even well inland away from the storm. Some factors that can make storms even more destructive are if they occur at the same time as high tide. In some areas, the tidal variation might be meters. So if you've got a couple of meters of storm surge on top of high tide, that would be a lot more destructive than if the storm surge is sort of canceled out by low tide. So all these factors are important to be aware of, and there, fortunately, in the United States are sort of sophisticated weather forecasting services like the National Hurricane Center. If you Google NHC, you can get up-to-date, really accurate hurricane forecast, and you're probably already doing that for Hurricane Milton, which is approaching now as I record this lecture. But pay attention to what the expert meteorologists say about the dangers of hurricanes, because they can and do destroy homes and businesses and can kill people. So be careful. This picture in the diagram here is the destruction caused by the first hurricane that I ever experienced, which was Hurricane Isabel in Virginia in 2003. So this is a pier onto the Chesapeake Bay, which is associated with the Virginia Institute of Marine Science, where I got my PhD. And the pier was entirely destroyed by giant waves that the hurricane drove into Chesapeake Bay. So hurricanes can hit a lot of different places, and you should always, always take hurricanes seriously. All right, that's all that we have for this lecture. I hope everyone stays safe in this hurricane, and I'll see you again soon. Bye-bye.